All right. Good afternoon. So let's continue on fatigue. We are on fatigue analysis on chapter 6. First thing that we should know is fatigue strength versus yieldless strength. For the yieldless strength or ultimate strength for any specified material, for example, AISI 1030 or 1045. So you go to the table and read SY, S ultimate. If the ultimate for tensile is different than compressive, you can get the numbers. But what would be the fatigue strength? Fatigue strength is defined by SN curve. It's very important curve on fatigue analysis. Suppose you would like to find fatigue strength for one specific material, AISI 1030. What you are going to do, you first make a test specimen like this, made of that material that you are looking for its fatigue strength. It should have this specific dimension. So these are the specification of test specimen. Standard dimension. It should be machined. This test specimen should be machined and polished. And then you apply pure bend, completely reverse bending moment. So the load that you apply is pure bending moment, and it's gonna completely reverse. We talked about that. It should move like the sine function. And it's working at the room temperature. So then you apply the bending moment with different value of that. So this bending moment is going to make the different value of the bending moment stress. And then you count number of cycles before the failure occurs on this test specimen, or before it breaks. So then you make a table, sigma versus n. Suppose here the first test that you are going to run, it's going to make the normal stress equals to the ultimate strength. So whatever is the ultimate strength for this material, you apply the normal stress, bending moment such that it provides sigma equals to S ultimate. You expect that after one number of cycles, it's going to fade. Then on the second test, you pick another test specimen, you apply a new sigma, which is less than this. Suppose this is 100. Second one you pick 110. Then you count number of cycles and write it down here. So after 50 number of cycles, it's gonna see the failure. Then on a curve with n as a number of cycles and this as a sigma, or we call it fatigue strength, just find this spot. If you do that, for ferrous material, ferrous material would be the materials which they have iron on it. So you are going to get something like this. Number of cycle versus SF is going to changing like this. For non-ferrous material, you will find something like this. So let me start talking about ferrous material, then I'll go through the non-ferrous material. For ferrous material, you will see a knee here. We call this point as a aspirin E, or endurance limit. This is S ultimate. And I call this, or name it as a aspirin L, this point. Aspirin L, S ultimate, aspirin E. The number of cycles for this point is around 1,000 cycles. And for me, it's about 1 million cycles. So for any ferrous material, AISI 1030, 1045, 1050, or any other ferrous material, you can get different curve, but it's going to look like this, with the different S ultimate, different aspirin E, and different aspirin L. Now, it's going to tell me if I apply bending moment to this test specimen, which makes this stress, suppose this stress, SF. This test specimen, it's gonna run for n prime number of cycles, and after that it's gonna fail. So this is what I can get from this curve. So this is one thing that you can learn from this curve. Endurance limit is defined as the largest amount of fluctuating stress that you can apply without any failure. Or we can say infinite cycle. So the endurance limit is defined as the largest amount of stress that you can apply to this specimen without having any failure, or it's gonna run forever. So any stress larger than aspirin E is gonna have limited life. So for that reason, I define two regions. Finite life after that, infinite life. From 1 cycle to 1,000 cycles, we call it low cycle. And after 1,000, we call high number of cycles. So these are some definitions that we can make for non-ferrous material. These are what we cover on Thursday class. This graph is representing that one. Low cycle from 1 to 1000. After 1000 is called high cycles. And finite life is going to define from 1 to 1 million cycles. I mean, it's about 10 million, but no, it's about 1 million cycles. Sorry. Pardon? Some references define 1 million as a finite life, some other define 10 million, but we work on 1 million, which is 10 power 6. So up to this point is called finite life. After that. If you compare this one, which is for non-ferrous material, with this one, for non-ferrous material we don't have any need. So it means you cannot find any endurance limit. So something like this. This is for the aluminum, different types of the aluminum. This curve is for one aluminum, this is for another one. The other lines for different types of aluminum. You have number of cycles versus fatigue strength. So you can tell me how many cycles do you want. For example, 1 million cycle for this material. The fatigue strength is going to be about 9 kpsi. If you want 100k, then it's going to be about 13 kpsi. So we don't have any endurance limit for non-ferrous material. If you look at back of the book for non-ferrous material, table 824, this is for aluminum. Table 824 has this information for cast iron, titanium, and aluminum. This is for the aluminum. So there is one column with fatigue strength. So suppose we have route to 2017. It's showing me that SF is 90 kpsi. What does it mean? It means for N equals to 500 million cycles. If you want to have 500 million cycles, this is the largest amount of fatigue stress that you can apply. So the numbers that you can see representing the number of cycles equals to 500 million. So it doesn't have any endurance limit, but this column is representing fatigue strength for a specific amount of number of cycles, which is 500 million. For ferrous material, we have many ferrous material. If we do the test and we find aspirin E, find aspirin E for different ferrous material. If you, for different material, if you plot S ultimate for that material versus aspirin E, you will get some dots. Like this. If you fit a line, it's gonna look like this. So this fit is the estimation of aspirin E as a function of S ultimate. So if the non-ferrous material that you have has S ultimate less than 200 kpsi, you go to the first line, multiple S ultimate by 0.5, and find aspirin E. So this is how you can find endurance limit for ferrous material. But if it's greater than 200 kpsi, no matter how much would be its ultimate, it's gonna be 100 kpsi. So which is representing this line. So before that, it's a half. After that, it's gonna be 100. I'm trying to find each point. S ultimate, I know where it is. S prime E now, I know how I can find the value for S prime E. Now I would like to find S prime L, which is corresponding to 1000 cycles. What would be the fatigue strength? S prime L can be calculated by this. F times ultimate strength. What is the F? These are coming from experimental test. We call F as a fatigue strength fraction. This figure, which is figure 618, is gonna give you the fatigue strength fraction. Just read S ultimate for that material. For example, if it's 140 kpsi, go up, it's less than 0.81, I can read 0.815. So for S ultimate equals to 120, I can read F equals to 0.815. Then multiply 0.815 by S ultimate and find S prime F. So now I'm gonna have all information about those key points, the knee points and the other 2 points. Any questions so far? Next step, I'm gonna find the equation for these lines. Then you can expect or estimate the number of cycles for a given stress. So if you are given with the stress, suppose this, you can find or expect how many cycles is gonna run based on that stress. So we have 2 lines, this line and this line. I'm gonna find the equation for this line, and for the homeworks problem, you are supposed to find the equation for low cycle region to connect SF, which is the fatigue strength, to number of cycles. So for N between 1000 cycles and 1 million, I'm going to find the equation between SF and number of cycles. If you look at this, it's a log-log curve. So it's a log function. It's not increasing as a term of 1, 2, 3. It's increasing as a term of 10 power 0, 10 power 1, 10 power 2, 10 power 3, 4, 5, 6, and also this one. So if this is the case, and you can see the log-log curve, it's gonna look like a linear function. You can see it's a linear function. So it's gonna tell me SF is gonna look like something like this. A n power b. How do I know that it's gonna look like this? Because the log-log function is a linear function. If you log both sides, log of SF would be log of a n power b, or log of a plus b log of n. So log of s as a one variable, y, log of n as another variable like x, y is a linear function of x. So the fatigue strength should look like this as a function of number of cycles. Point 1 has n equals to 1,000 cycles. This point has 1,000 cycles, and SF is going to be S print L, which is F times S ultimate. F times S ultimate. Point 2 is the knee point with 1 million cycles and S print E. So I have two information I can plug in here, solve for A and B. Two equations, two unknowns. Let me plug in there. Log of Fs ultimate equals to log of A plus B log of n is 10 power 3. Log of 10 power 3 is going to be 3 log of 10, which is 3. So log of A plus 3B. First. Second equation is going to be log of S spring E equals to log of A plus B log of 10 power 6, which is log of A plus 6B. F is given, S ultimate is given, S print E you can read from that equation. So we are solving for A and B. So if I subtract these two, I will get log of subtract F S ultimate minus log of S print E would be, these two can be cancelled out, 3B minus 6B, negative 3B. So B would be negative 1 over third. Log of Fs ultimate minus log of S print E would be log of Fs ultimate divided by S print E. So I could find B. Negative 1 over third F S ultimate divided by S print E. You remember on log of X minus log of Y is log of X divided by Y. So this minus this is going to be this divided by S print E. So you can find B. How can I find A? Either you plug in there, or this equation you can find log of A. If I do that, this is B. How can I find A? Suppose I plug in there. Log of Fs ultimate would be log of A plus 3 times B. 3 times negative 1 over third is going to be negative log of Fs ultimate divided by S print E. So log of A would be this plus this. Plus log of X plus log of Y is the multiplication of these two. So this plus this, meaning Fs ultimate times Fs ultimate divided by S print E. Log of A would be log of F print S Fs ultimate square divided by S prime E. We can cancel out log. A would be Fs ultimate square divided by S prime E. So now you have this equation. SF equals to A n power B. If I tell you what would be the fatigue strain if I want to have 10 power 4 cycles, I would like the test specimen run for 10,000 cycles, what would be the fatigue strain, or what would be the largest amount of stress that I can apply for this number of cycles. 10,000 is between 1,000 and 1 million. Just plug it in over there. A and B are given, solve for SF. Or I can say for a given sigma reverse, you apply bending moment. That bending moment is going to generate normal stress equals to sigma. The reverse meaning that I have reverse cycle. So for this number, for this stress, how many cycles? How many cycles it will run? So what you need to do, just set sigma reverse equals to SF, A times n power B, sigma reverse divided by A, n power B. How can I find n? Just apply the log. Log of sigma reverse divided by A would be log of n power B. B is coming out of the log. Divided by B, 1 over B, log of sigma reverse divided by A. Then 1 over B, it's gonna be the power of this one. So I can write sigma reverse divided by A power 1 over B equals to number of cycles. So for this normal stress that you apply, it's gonna run for that number of cycles. This is the application of this equation. For a given number of cycles, find the fatigue strength. For a given completely reverse cycles, you will know for how many cycles it's gonna run. And it's valid for this region. For this region, you should get the new A and B. And the new homeworks, you need to find the A and B for that region. Question on this. This chapter has many details, so it's just the beginning of the fatigue. So you will see many equations, many parameters, and many details. So make sure that you are following the material, and if you have any question, just ask before it's getting too late. Equation 616 is the equation that I have here. For a given sigma, find the number of cycles. Again, it should be for this region. For the different region, which is this, you should use different value of A and B. All right, let me work on one example. So for the steel of 1050 hot roll, find endurance limit aspirin E. There is a reason that I use prime for this because later on I'm going to talk about SE, which is a modified value of aspirin E. So here we have aspirin E, then I'm going to modify this to SE for different case. The first thing is find endurance limit for this material. Second part, we find the fatigue strength for the test specimen which is under 10,000 cycles. So if the test specimen is made of this material, we would like to have 10,000 cycles. What should be the fatigue strength for this number of cycles? And part C, if the test specimen is under 55 kpsi, completely bending moment stress, find the number of cycles. Before it fits. So we would like to do this. So first, find the endurance limit, aspirin E. To find the aspirin E, I should use this equation. It's a ferrous material, it's a steel. So if S ultimate is less than 200, aspirin E is 0.5. S ultimate, if S ultimate is less than 400. So let's look at for 1050 is here, hot roll. This column is tensile strength, which is S ultimate. This is for yield strength, which is SY. We are looking for S ultimate. For 1050 hot roll, is going to be 620 MPa or 90 kpsi. So S ultimate is 90 kpsi. 90 is less than 20, 200 kpsi. I can use this. Aspirin E is 0.5 times 90 is 45 kpsi. The equation that I showed you, it has two versions. one for MPa or megapascal or SI unit, the other one is US unit, which is kpsi. So make sure that you are consistent when you are using this equation. So 45 kpsi is the knee point. This point is 45. Now, second part is asking find the fatigue strength for the test specimen, which is under 10,000 cycles. This region is between 1,000 and 1 million. So 10,000 is going to be somewhere here. So I should find this equation. To find this, I should find A. A is here. I need to read F. Fatigue strength fraction. S ultimate is 90 kpsi. Go up, it's about 0.86. So figure 618, F is 0.86. So I know this. S ultimate is 90, S20 is given, so you can find A. 0.86 times S ultimate. S ultimate is 90. Don't forget to change it to PSI. Don't say that these two they can be used as the same unit because this one has a square, this one doesn't have. So make sure that you use PSI, not kpsi. So 90 kpsi divided by S20, which is 45 kpsi. You will get 133.1 for A. kpsi. The unit is psi. If you do the math, you will get 133.1 times 10 power 3. If I change it to kpsi, is 133.1. So this is the value for A. The value that you will get here is going to be 130.1 times 10 power 3 psi. I just changed it to kpsi. These are the common mistakes that I have seen. So next one is finding B. Negative 1 over third log of Fs ultimate (90 kpsi). Here you can use kpsi if you want, because this divided by S20, 45. I just want to be consistent. I'm using yes. So B is gonna be negative 0.0785. You have A, you have B. For 10 power 4, SF would be A, 133.1 kpsi, 10 power 4, negative 0.0785. If you do calculation, you will get 64.6, whatever is the unit of this, which is kpsi. So if you want to run this test specimen for 10,000 cycles, the stress that you should apply is 64.6 kpsi. Any question on this? I'm done with this, the first two parts. Let's look at part C. If the test specimen is under 55 kpsi. So this point is F, which is 0.86 times 90. It's more than 72. So 70, for example, 3. So 55 is between 45 and 73. It's gonna tell me I'm gonna be on this region where this equation is valid, because 55 is between 45 and 73. Suppose if this one was 50, then 55 is greater than 50, so I'm gonna be on the first region. So you should be careful which region you are in. So to find n, to find number of cycles, I'm gonna use this equation. What would be the number of cycles when sigma reverse is 55? To apply that, kpsi divided by A, which is 133.1 kpsi power 1 over B, zero 785. $77,500 cycles. So this test specimen under this loading, it's gonna run for 70, almost, about 78,000 cycles. If I tell you the speed is 1 revolution per second, you can figure out how many seconds or how many hours it's gonna work. 77,500 seconds. So then change it to the hour. It's gonna tell you for how many hours this component or this system is gonna run. So you can expect the life of this test specimen. Makes sense? All right. What you will see on textbook or handbooks for different material, for different ferrous material, is going to be the SN curve. This SN curve is based on this criteria. We should have a standard dimension. The surface should be machined and polished. We should have completely reversed bending moment. It should work at the room temperature. So these are the conditions that this graph is based on that. But in reality, the component that you might have different dimensions. You might have component with different surface conditions. They might be unpolished, they might be ground, not machined, so we might have different conditions. You might have different type of the loading, not pure bending moment, you might have pure torsion, or even not completely reversed, something like this. It's not completely reversed because it's not going to see the zero. And the room temperature might be different. So for those reasons, we should modify endurance limit. The endurance limit that I can get from this curve should be modified. This S squared E. How can I modify that? I'm gonna talk about the modification factor based on each of these criteria. The modified value of the endurance limit is gonna be the multiplication of this factor to aspirin E. You know how to find aspirin E? Aspirin E is coming from that curve or that equation that we talked about, that it's for the test specimen case. Ka is considering the surface condition modification factor. If your component has different case, has different surface condition, then you are going to talk about Ka. If your component has different size, you are going to talk about the different dimension. We call Kb to modify that. If the load is different than the Q bending moment, we are going to look at Kc. Kd is going to be temperature. Ke, reliability factor. I will talk about that when we go through that factor. And Kf would be the other modification factor that we don't discuss in this course, but you might have different modification to be considered. So after you find all factors, you can multiply them and find the actual or the correct value for the endurance limit for the components which is under fatigue loading. So on Wednesday, I'm gonna talk about each single factor and how can we get them.